Welcome back. Today we're going to be talking about a compound that you may have had some direct experience with in your own life. In fact, it might be a substance that is so familiar to you that you might not really recognize what an extraordinary and unusual molecule water actually is among compounds on Earth because you're so used to the way it behaves. But water is really actually very unusual. So water is absolutely critical to life functions. Life first evolved in an aquatic environment in the early oceans. And it's absolutely essential for all of the biochemical reactions that go on in living things. But in addition, water is the only common substance that exists in the natural environment in all three physical states of matter. Ice, water, and steam are all very common on Earth. And water also has unique emergent properties. So remember, this is a major theme this semester, that things, when you put them together, are going to behave differently than the individual components of that thing. This is what we mean by emergent properties. And these emergent properties of water help to make Earth suitable for life. Also, the structure of water molecules allows them to interact with other molecules. So this is familiar from our last section on the basic chemistry of life, this idea of electronegativity and the fact that because oxygen atoms attract electrons more strongly than hydrogen atoms do, that there are these partial charges on the oxygen and hydrogen atoms in the molecule. And these polar covalent bonds between oxygen and hydrogen mean that there are these partial charges that attract each other. And we talked about hydrogen bonds in the last section, the positive and negative areas on the water molecules attracting each other. And this tendency to hydrogen bond quite strongly, I mean, it's still not a strong bond in the way a covalent bond is a strong bond, but more so than hydrogen bonds with a less electronegative atom involved, such as nitrogen. Oxygen is the most electronegative of the atoms that are important to biology, and hydrogen is one of the least. So these bonds are really pretty polar. The tendency to make these strong hydrogen bonds makes water behave in very unusual and interesting ways. So as a result of this tendency to form these hydrogen bonds, we see four emergent properties of water coming about that contribute to Earth's suitability for life, for water being such a great molecule for supporting life. So four of water's properties that facilitate life on Earth is, and we'll talk about each of these individually, so I'm not going to say very much about them at this point. I'm just going to list them. Cohesive behavior, the ability to moderate the temperature of the whole surface of the Earth. Expansion upon freezing is a very unusual property that water has that turns out to be very important for the evolution of life on Earth. And also that it works so well as a solvent, so things dissolve in it. Again, we'll talk more about each of these as we go through. So let's start with cohesion of water molecules. What does that mean? That means water molecules are kind of sticky. They stick together more than other molecules in a liquid would. So collectively, all of these hydrogen bonds that are constantly forming and breaking and reforming hold water molecules together even though it's a liquid. The fact that they break and reform keeps the water in a liquid state and behaving like a liquid, but these bonds, when they're in place, cause water molecules to generally stick together, and this is called cohesion. So cohesion is partially responsible for this transport against gravity through plants. This is one of the big questions that I said on the syllabus we are going to answer for you this semester. So this is just part of the answer, is the cohesion of water molecules allows molecules of water that are out on the leaves to pull up as they evaporate away They pull up on the water molecules just underneath them, which pull up on the water molecules just beneath them, and everything gets pulled up, and sometimes to very, very great heights against gravity due to the fact that these water molecules just stick together due to these hydrogen bonds. Adhesion is a similar idea. It's due to the hydrogen bonding of water molecules, but this time the water molecules are forming hydrogen bonds with something that's not water, so some kind of substrate. So this is another part of the answer about how water can be transported up against gravity in these trees and in plant stems, is that not only are the water molecules sticking to each other, but they're also sticking to the sides of these transport vessels that run through the plant. Again, much more on that as we go into plant physiology. But that's going to help to support that mass, that it's sticking both to the water molecules that are pulling from above and also to the walls, and this is called capillary action. So adhesion and cohesion are also responsible for some of the other familiar but unusual behavior of water as compared to other liquids. So this tendency, if you slightly overfill a glass, to rise up a little bit over the level of the edge of the glass. This is due to the water molecules at the surface sticking together and not wanting to spill out into the air. Again, when I say wanting to, we're talking about a tendency, not a desire, but tending to stick together rather than escaping out into the air. And at least until you overfill it too much, those molecules are going to tend to stick together and form a little bit of a bubble over the surface. Adhesion is responsible for this phenomenon that we see often in chemistry when we're measuring out liquids in narrow cylinders. This meniscus, this little bit of a concavity at the surface of the liquid, is due to water sticking to the sides of that measuring vessel and causing them to rise up a little bit. So remember, always measure to the bottom of the meniscus. Another phenomenon that arises from the cohesion of water molecules is surface tension. The tendency of the surface of the water to resist a little bit of force before the water molecules will separate from each other and allow the object to sink. So very small, lightweight insects can often do this trick of walking on water because of this surface tension that's going to resist the tendency to separate those water molecules from each other due to the hydrogen bonding. All liquids have some level of surface tension, but water has an unusually high surface tension due to these hydrogen bonds between the molecules, and the molecules will tend to stick to each other. Another emergent property of water is the moderation of air temperatures and also the resistance of water itself to change temperature. So that maintains the water and the air on Earth at a steady, relatively stable temperature within the limits of what life can withstand. So water absorbs heat from air that's warmer than it without changing its own temperature very much, and also can release a lot of stored heat to cooler air. So for example, it'll absorb a lot of heat from the air during the day when it's warm outside, the sun is out, and be able to release that stored heat back into the air at night when the air is cooler. And all of this with very minimal change to its own temperature. So before we go into the details of why this happens, let's think a little bit about what we actually mean by these terms, temperature and heat and thermal energy. So remember that kinetic energy is the energy of motion. So we talked about converting potential energy due to height into kinetic energy, the energy of the motion, say, of a ball rolling down the hill, converting that potential energy to kinetic energy. But kinetic energy isn't just directional movement, it's any kind of motion. So if you think about the random movement of molecules, the faster they're moving, the more kinetic energy they're going to have. And even just the vibrations of molecules, say within a solid, that vibration is kinetic energy. Every molecule has some kinetic energy unless it gets all the way down to a temperature we call absolute zero, which is where all kinetic energy stops, and that is a very, very, very low temperature. The kinetic energy associated with the random motion of atoms or molecules is called thermal energy. So anything that is not directional movement, for example, as a result of a force being applied, anything that's just the random motion of atoms and molecules, this contributes to thermal energy. When we say temperature, what we're talking about is a measure of the average kinetic energy of those molecules. So it'll depend on how fast they're moving. When thermal energy is transferred from one body of matter to another, we refer to that as heat. So remember, heat is thermal energy being transferred from one thing to another. And we can measure the amount of heat in terms of a unit called a calorie, and we're going to define a calorie as the amount of heat, so the amount of thermal energy that needs to be transferred to water in order to raise the temperature of 1 gram of water by 1 degree Celsius. Conversely, if it takes 1 calorie to raise the temperature of 1 gram of water by 1 degree Celsius, it's also going to release that amount of thermal energy when it cools down by 1 degree Celsius. So same amount of energy in as out. And just a note, the calories that you see on food packages are actually kilocalories. The calorie unit is way too small, and we would think that we were eating way too much energy if we actually measured it in real calories. So those are actually kilocalories, but we call them calories for simplicity. The joule is the metric or SI System International unit for energy, much more commonly used in physics, in the field of biomechanics. You would see joules a lot more often than you would see calories, but it's another way of measuring that thermal energy transfer. So I mentioned that water is very resistant to changes in its own temperature, and we call this resistance to change in temperature specific heat. So the specific heat of a substance is the amount of heat, so remember that's transfer of thermal energy, that must be absorbed or lost for 1 gram of that substance to change its temperature by 1 degree Celsius. As we just saw, the specific heat of water is 1 calorie. We said it takes 1 calorie of energy to change 1 gram of water by 1 degree Celsius. So that is just how we've defined a calorie. So the specific heat of water is relatively high compared to other substances. You'll see some examples of the specific heat of other substances in your book. When you're cooking something on the stove, long before the water or the food, which will consist of mostly water, is even hot enough to eat, you can burn your finger on the pot that you're cooking it in, because that pot is going to have a much lower specific heat. It's going to change its temperature a lot more in response to the energy that's being added to it than the water is. You might have also noticed when you're waiting for a meal to cool down to the point where it won't burn you, things that have less water content, like things like bread, are going to cool down a lot faster because they have less water in them than something that has more water content. So why does it have such a high specific heat? So the reason for this is this tendency to form hydrogen bonds. So heat is absorbed when hydrogen bonds break, and heat is released when hydrogen bonds form. So the way to think about this is basically before it's going to change the amount of random motion the molecules are going through, you have to break a whole bunch of hydrogen bonds before that can happen. So the energy it takes to break those bonds has to be absorbed before it's going to start changing the kinetic energy of those random movements of the molecules. So similarly, as the temperature is decreasing and that thermal energy, those random motions are slowing down, a bunch of energy is going to go into forming more hydrogen bonds before the random motions of those molecules actually slow down. So this high specific heat of water minimizes temperature fluctuations. It takes a lot of energy to actually change the temperature of water. And we can see examples of this stabilization of air temperatures if you look at coastal climates versus inland climates. So I am from the West Coast originally, so I'm very familiar with this phenomenon right on the coast. The closer you live to the coast, the more stable temperatures tend to be year-round. You get year-round temperatures ranging between 60 and 80 or so. Whereas if you go farther inland, you get much higher temperatures in the summer and also lower temperatures in the winter. And this is because the ocean is absorbing all of that heat during the day and taking it out of the air and then releasing that heat back into the air at night. As the air cools down, the water starts to release that heat, and it does that with a minimal change to its own temperature. Another biological consequence of these properties of water is the ability for organisms to use evaporative cooling. Evaporation or vaporization is the transformation of a substance from a liquid to a gas, so we all know what it means for something to evaporate. And this absorbs energy. So the heat of vaporization is the heat a liquid must absorb for 1 gram to be converted to gas. So as water evaporates, the water molecules that have the highest energy already are the ones that are going to be the most likely to escape and evaporate off, which means that every time some of those molecules with the highest energy escape, the average energy, the average thermal energy in the ones that are remaining is a little bit lower. So one way you can think about this is if all of the fastest runners on the junior varsity track team all get moved up to the varsity team, the average running speed of the junior varsity team is going to be lower as a result of those fastest kids leaving and moving up to the other team. So many animals use this evaporative cooling. For example, when dogs pant, they are using evaporative cooling through their mouth to cool down their body. When we sweat, we're using evaporative cooling to cool down our body surfaces. Another important emergent property of water that is also a result of its tendency to form hydrogen bonds is the fact that ice floats on top of liquid water. And this may not seem the least bit extraordinary to you because you're so used to this phenomenon, but really in most substances, the solid form of them is much more dense than the liquid form. This is the normal state of things. You always think of solids as being more dense than liquids, but not the case with water. So ice floats in liquid water because hydrogen bonds in ice are more orderly. They're more regular. This orderly arrangement of these hydrogen bonds keeps those water molecules spread out from each other a little bit more, making the ice less dense. So water reaches its greatest density at about 4 degrees Celsius. As it goes down between 4 and 0, it's going to start decreasing in density. And so here's what happens. In the liquid form at higher temperatures, the molecules are slipping past each other, they're forming those hydrogen bonds and breaking them, and it allows them to pack fairly tightly to one another because more than one hydrogen can come and associate with this oxygen, and they're going to be making these hydrogen bonds a little bit less rigidly because they're moving a lot more, they're moving past each other. When they stop moving quite so much, these hydrogen bonds become stabilized so that each oxygen is making 2 and only 2 hydrogen bonds with a hydrogen, and those bonds are going to be stable. So these water molecules are going to be held at a little bit more of a distance from each other now that they're not moving past each other and breaking and reforming these bonds all the time. So this regular pattern of hydrogen bonding is going to keep these water molecules a little bit further away from each other, and that means that the ice is going to be less dense than the water, where the water molecules are more closely packed together and sliding past each other. So what does this mean? This means that you get a layer of ice that forms at the surface, and you're still going to have liquid water underneath that. So living organisms can continue to survive in this liquid environment even when the surface of the water freezes over. And if you think about that, this is extremely important for the evolution of life. If ice was more dense than water and it tended to sink to the bottom, as soon as water started to freeze, it would continually sink down to the bottom, and eventually all of that body of water is going to be frozen completely solid and nothing could live in it. So this is a very, very important emergent property of water. The final emergent property we're going to talk about is the use of water as a solvent. Okay, so water tends to form solutions. So a solution is a liquid that's completely homogeneous mixture of substances. So equal concentrations of solutes throughout. The solvent is the dissolving agent of a solution. So in the case of these aqueous solutions, the solvent is water. The solute is the substance that is dissolved in the water. So these molecules that are dissolved. And an aqueous solution is one in which water is the solvent. So just some definitions there. And let's take a closer look at how these solids actually dissolve in water. So water is a versatile solvent due to its polarity. So it's got these partial positive and negative charges on it that can be attracted to positive and negative charges on ions. So when an ionic compound is dissolved in water, each of these ions, starting from the surface and working in, is gradually surrounded by water molecules, and in particular the parts of the water molecules that are attracted to their charge. So we see in the case of chloride, we've got the hydrogen sides of these water molecules surrounding the chloride ion. And in the case of positively charged sodium, we've got the oxygens clustering around and surrounding that sodium ion. And we call this surrounding group of water molecules a hydration shell. A hydration shell. And this is two-dimensional, but you can think of this as a little ball of water molecules, three-dimensional, that completely surrounds these ions. Water can also dissolve compounds made of non-ionic polar molecules. So molecules that are covalently bonded but also have these partial positive and negative charges in places on the molecule. Even fairly large polar molecules such as proteins can dissolve in water if they have enough polar regions on them. So when this happens, if there are nonpolar regions, they're going to tend to fold to the inside. These polar regions are going to be folded to the outside where they come in contact with water because they're attracted to the polar water molecules. And here's an example of a very large molecule being completely surrounded by these little polar water molecules, and you can see that different regions of this molecule can have different partial charges. So here is a part that would be positively charged, attracting the oxygen side of that water molecule. Over here is probably a region that's negatively charged, attracting those hydrogen atoms with their partial positive charge, and then when the water molecules completely surround it, then that molecule is dissolved in the water. So this gives us the concept of hydrophilic and hydrophobic substances. So a hydrophilic substance is one that has an affinity for water. Why does it have an affinity for water? Because it also has polar regions that are going to attract the polar regions on the water molecule. A hydrophobic substance is one that does not have an affinity for water. One often hears the expression that oil and water don't mix, and we've seen this when we try to make a vinaigrette dressing. The water-based hydrophilic vinegar separates from the hydrophobic oil. A common misunderstanding is that a hydrophobic substance actually repels the water, and the name hydrophobic actually suggests that. Phobic means fearing. But really, nonpolar molecules aren't particularly attracted to or repelled from water or even other polar molecules. They have no electrical charge, and so they have no particular affinities for other molecules. So when we think of a polar molecule sort of staying away from polar molecules, that's really the result of the polar molecules' affinity for each other, and they tend to cluster together and exclude those nonpolar molecules. So an analogy that you might have in your head for this is, imagine a party where half the people all know each other. Everybody knows everybody else for this half of the group. And then the other half of the group, nobody knows anybody at this party. They're just come in and they'll talk to whoever they happen to bump into. So all these people who all know each other are going to tend to cluster together and all chat together, these people who don't have any particular attraction or repulsion for anybody in the room are going to be kind of separated out due to the clustering of the in-group. And it's not that they don't want to talk to those people. It's not that they have any particular desire to talk to the other people who don't know anybody. It's just that they have been kind of pushed aside by all these people who all know each other. So oil molecules are hydrophobic because they have nonpolar bonds. So this idea of the oil separating out from the vinegar, again, the vinegar excludes them. And hydrophobic molecules related to oils are the major ingredients of cell membranes. And so this is going to be an important part of that regulation of the movement of materials in and out of the cell. They're going to resist the movement of polar molecules. So let's start to think about the materials that can be dissolved in water. So most chemical reactions in organisms involve solutes dissolved in water. So we can think of the cell as being a little beaker where you're going to dissolve something and those things are going to react. So in carrying out experiments, we use mass to calculate the number of solute molecules in an aqueous solution. So the thing to keep in mind is when thinking about the concentration in these aqueous solutions, what matters is the number of molecules. The mass of the solute in and of itself doesn't matter. The volume of the solute that's in the water doesn't matter. You can have the same number of very small molecules as the number of much larger molecules, and you still have the same concentration, even though there's more matter in the large molecules. We use the mass to calculate the number of molecules in the aqueous solution because the number of molecules is what matters to the concentration. So to figure out the number of molecules in a certain mass of solute, we use the molecular mass. And so the molecular mass is the sum of all the masses of all the atoms in a molecule. So remember, the atomic number is equal to the mass of that atom in Daltons. And then the number of molecules are usually measured in mole, where 1 mole equals 6.02 times 10 to the 23 molecules, which is also known as Avogadro's number. Avogadro's number and the unit Dalton were defined such that 6.02 times 10 to the 23 Daltons equals 1 gram. The molecular weight in Daltons of your molecule is going to be equal to the mass of 1 mole of that compound in grams. So the measure that we usually use of the concentration of a solute in an aqueous solution is the number of moles of solute per liter of solution. So it's not per liter of water. You mix the water and the solvent together to make 1 liter combined, and then the molarity is the number of moles of the solute in that 1 liter of mixed solution. The third concept in this chapter has to do with acids and bases and understanding how those affect reactions in aqueous solutions. So this is very important to living organisms because the physiological functions in living organisms occur within a fairly narrow range of acidity. A hydrogen atom and a hydrogen bond between 2 water molecules can shift from one to the other. In other words, a hydrogen atom can be removed from a water molecule. So the hydrogen atom is going to leave its electron behind. Why? Because oxygen is much more electronegative than it is, and it's going to have a much higher affinity for that electron. And so when that hydrogen atom dissociates, it dissociates as just a proton. And we also call this a hydrogen ion. So the molecule that lost the proton is now an ion also. It's gained an extra electron, and we call that a hydroxide ion, and the symbol is OH-. So those protons don't actually just float around and continue to exist as protons. They're actually going to find another water molecule to join onto to form a hydronium ion, H3O+. But the way we usually talk about this, it's cumbersome to use the H3O+ and call it a hydronium ion. So we just use shorthand and refer to it as a proton or a hydrogen ion, and we just call it H+. But keep in mind that generally these H+'s are in the form of a hydronium ion, H3O+. Water is in a state of dynamic equilibrium in which water molecules dissociate at the same rate at which they're being reformed. So we saw this equilibrium concept in the last chapter. So here is that equilibrium equation. We've got the forward reaction of a hydrogen atom, a proton, being transferred to another water molecule to form hydronium and hydroxide. And when these two encounter each other, they're going to return back to the state of two water molecules. And this is occurring at the same rate. So we're going to have a constant concentration of these hydronium ions and hydroxide ions, even in pure water. So most of the time, most of the water molecules are in the form of just plain water molecules. This dissociation of water molecules is statistically rare in the sense, it happens all the time, but in terms of the total number of water molecules out there, it's pretty rare. And so the concentration of these hydronium ions, these protons, and hydroxide ions is going to be fairly small, but changes in these concentrations and the dissociation of water molecules is going to have a huge effect on organisms. As I mentioned, these physiological processes occur within a fairly narrow range of pH. So changes in the concentrations of hydrogen and hydroxide ions can drastically affect the chemistry of a cell and the physiology. So in pure water, the concentrations of hydrogen and hydroxide ions are equal. But adding certain solutes called acids and bases is going to modify the concentrations of hydrogen ions and hydroxide ions, and they can be different from each other. When you add an acid, it's going to increase the concentration of hydrogen ions. If you add a base, it's going to increase the concentration of hydroxide ions. So biologists use a scale called the pH scale, you're probably familiar with it, to describe whether a solution is more acidic or more basic. More definitions: an acid is a substance that increases the proton concentration of a solution. A base is a substance that reduces the proton concentration. It does that by adding hydroxide ions, which then combine with those protons to create water molecules. So it's going to reduce the proton concentration in the solution. Strong acids and bases dissociate completely in water. If we think of a chemical equation where something like hydrochloric acid, HCl, is dissociating in water, so we've got HCl as the reactant turning into the products H plus and Cl minus, that reaction is going to go to completion. The arrow will be in one direction, and all of that hydrochloric acid that you add is going to be converted into the ionic form, the protons and the chloride ions. So that reaction will go to completion. Weak acids and bases reversibly release and accept back hydrogen ions, but can still shift the balance of protons and hydroxide ions away from neutrality. So as we said, in pure water, the concentration of hydrogen ions and hydroxide ions is equal, and it turns out that in any aqueous solution at 25 degrees Celsius, the product of the hydrogen ion and hydroxide ion concentration is going to be constant, and it's going to be equal to 10 to the negative 14 molar. The hydrogen ion concentration's molarity, if you multiply it by the hydroxide ion concentration molarity, they're going to multiply together to equal 10 to the negative 14th molar. So the pH of a solution is defined as the negative logarithm of the hydrogen ion concentration. And we write that as pH equals the negative log of the concentration. So these brackets, these square brackets, indicate concentration in molarity. For a neutral aqueous solution, the concentration of hydrogen ions is 10 to the negative 7th. It has to be, because we know in pure water the concentrations of hydrogen ions and hydroxide ions are going to be equal to each other, and if they have to both multiply to 10 to the negative 14th, they have to both be 10 to the negative 7th. So the pH is negative 7 equals 7. Because of this negative logarithm, the more acidic something is, the lower its pH value. So acidic solutions have pH values less than 7. Basic solutions have pH values greater than 7. And most biology occurs in this range right here, very narrow part of the pH range from 6 to 8. So here we have seawater, it's a little bit basic, or a little bit basic inside the small intestine. Pure water, human blood, tears are all at around a neutral pH. Urine tends to be a little bit acidic. A lot of things that we ingest into our bodies are fairly acidic. But this means that if you know the pH of a solution, you can compute both the concentration of hydrogen ions and hydroxide ions. So just as an example, for lemon juice, the pH is -2, so that means the concentration of hydrogen ions is 10 to the -2 molar equals 0.01 molar, and so we know that the concentration of hydroxide ions is 10 to the -14th divided by 10 to the -2. Remember, when you're dividing powers of 10, you just subtract the exponents, so we get 10 to the -12th molar. So a much higher concentration of hydrogen ions than hydroxide ions. So we talked about these weak acids and bases that dissociate reversibly and release that proton, or accept that proton reversibly. So buffers are substances that minimize changes in the concentration of protons and hydroxide ions in a solution. So most buffer solutions contain a weak acid and its corresponding base, and they combine reversibly with these hydrogen ions. So an example from your book is carbonic acid. So when conditions are basic, the reaction is going to go more toward the forward reaction of dissociating that proton to balance the extra hydroxide ion concentration in the solution. But if things become a little bit more acidic, the reaction is going to go to the reverse reaction with this proton associating back with the bicarbonate ion HCO3- to form more carbonic acid. So this is going to keep things at relatively stable pH. This is the reaction that happens in your blood all the time when you are releasing carbon dioxide. So now let's think about the importance of pH in terms of the conditions on early Earth and how those conditions came to be within the range that can support life. So what we're looking at here is the surface temperature of the Earth, carbon dioxide concentrations, and water concentrations, either in the form of steam, of gaseous water, or of liquid water. And this is for the first billion years of the Earth's existence. So from the moment the Earth formed until about 1 billion years later. So very early in Earth's history, the Earth was being constantly bombarded by asteroids that were keeping the temperature of the Earth high. Once that bombardment stopped, then the Earth was able to radiate that excess heat away, and the surface temperature on Earth began to fall. So at this time, there's a lot of volcanic activity that kept the concentration of carbon dioxide in the atmosphere fairly high. And of course, because the temperature was very high, there was a fairly high concentration of water vapor and not much liquid water on the surface of the Earth. So as the surface temperature started to come down after the asteroid bombardment period, it's coming down just due to radiant cooling, of releasing that heat back out into space. And as the temperature starts to come down, we start to see more and more liquid water on Earth. So this is the period of time when we see the oceans forming. So as the ocean forms, some of this carbon dioxide starts to be absorbed by the ocean, both dissolving in the ocean and also forming rocks with calcium that it's picking up from mountains as it dissolves the rock in the mountains a little bit. The calcium is carried by rivers down to the ocean and converts the carbon from the carbon dioxide into calcium carbonate, which is then stored more or less permanently in the bottom of the ocean. So the ocean is absorbing some of this carbon dioxide. It's staying fairly stable in the atmosphere until we get to about this point. At this point, enough of that carbon is being taken up by this rapidly growing ocean that it actually starts to decrease in concentration in the atmosphere. Remember that carbon dioxide is a greenhouse gas, so it's going to tend to keep heat close to the surface of the Earth. But as its concentration decreases, the temperature of the Earth is also going to decrease because more of that heat is going to be released out into space. So you see this dramatic decrease in both carbon dioxide in the atmosphere. As we get more and more liquid water, more and more of that carbon dioxide is going to be sequestered into the oceans. The less carbon dioxide there is in the air, the more of the surface of the Earth can cool until we get this sort of crash of carbon dioxide levels, stabilization of the temperature. As the temperature stabilizes, the carbon dioxide comes back up a little bit to somewhere around current levels. And at this point, we've got sort of a stable equilibrium of carbon entering the oceans and being removed from the atmosphere at more or less the same rate. So we've got stable temperatures at this point, stable carbon dioxide, and also an abundance of liquid water as the temperature stabilized within this range of between 0 and 20 degrees Celsius. Remember, what's one of the consequences of having a lot of carbon dioxide dissolving into the water is that we get a lot of production of carbonic acid, which is going to create an acidic environment in the water. Even though it's a buffer, if you keep adding more and more to it, you're still affecting that concentration of hydrogen ions. Before life could emerge on Earth, those conditions had to be stabilized. And what we see is right around the time that temperature and carbon dioxide levels stabilized on Earth is about when we see the earliest evidence of life on Earth. So that introduces a concept called planetary boundaries, the range of conditions that are necessary on the planet to be able to support life. So as soon as the conditions were within those planetary boundaries, life emerged. So the struggle that we're seeing now is how to keep those conditions within those planetary boundaries. So as we know, we are releasing large amounts of carbon dioxide into our atmosphere through the combustion of fossil fuels. And this is having an effect on the acidity levels of the ocean. Carbon dioxide is the main product of fossil fuel combustion. Your book says about 25% of human-generated carbon dioxide. Elsewhere in the literature, I've seen estimates closer to 30 or 40% of that carbon dioxide is absorbed by the oceans. So a lot of that carbon dioxide is going into the oceans. For a long time, people thought that was a good thing because that's, it's going to get absorbed by the oceans. That's going to keep it from getting too high in the air. But what they didn't recognize is that's having a huge effect on the chemistry of the ocean. So carbon dioxide dissolved in seawater forms carbonic acid. And even though carbonic acid is a weak acid, it's still contributing to the overall pH of the ocean, which, remember, we saw seawater was slightly basic, so it's becoming less and less basic with this ocean acidification. So the carbon from CO2, it's going to combine with water to form carbonic acid, H2CO3. That carbonic acid is going to dissociate into a hydrogen ion plus bicarbonate. And so some of those hydrogen ions are going to associate with carbonate ions that are in the ocean to form more bicarbonate. But these carbonate ions are what is needed by marine invertebrates to form their shells, which are made of calcium carbonate. Calcium carbonate is this product here, which needs to combine with carbonate rather than bicarbonate to form. So the more of this carbonate that is taken up and transformed into bicarbonate, the less that is available for marine organisms to build their calcium carbonate shells, and it's having a great impact on things like coral reefs, shell thickness in many marine invertebrates. We're beginning to see a measurable effect. So it's one of those things we really need to think about. Keeping the Earth sustainable for life is keeping conditions within those planetary boundaries that are necessary. So finally, in conclusion, I just want to bring your attention back to this list of 4 important concepts, 4 important emergent properties of water that we've talked about. Cohesive behavior, very important to the behavior of water. for the ability of plants to transport materials through their stems and roots. Its ability to moderate temperature, again, it's keeping the Earth's climate within those planetary boundaries of stable temperature at which life can exist. Expansion upon freezing. Remember, if ice didn't float on top of water, we'd have a very big problem with oceans freezing solid when the temperature drops. And then also its use as a solvent for many materials, including acids and bases, very important to life processes. So from here, we're going to start thinking about another very important substance to life. We're going to be thinking about carbon. So if we think about the two things that are most critical for life to exist, we would have to say they're water and carbon. If you were looking for evidence of life on other planets, those are the two things you would be looking for. They're so important to life processes that the idea of life without those two things, it seems completely inconceivable.